homework. Then after the homework, after we go over the homework real quick, we will be doing the notes that I attached to today's lesson. So you might want to pull those up. Like I promised you yesterday, they are on tangents. Properties of tangents, theorems of tangents, and using those. Not many people joining us online today. There's another one. And another. For those of you just newly joining, we're going to go over the homework first. Should be pretty quick. So it was just basically identifying and naming parts of circles. We did number 1 yesterday in class. I tried to write all the different possibilities here, but I'm sure there might be some that I didn't write all the possibilities. So let me show you what I've got. And you can let me know if there's another one you need to ask on. Let's see. I think on this one, yeah, number 2, I listed all the possible right answers. So if your answer is not one of those, we have some issues. One that might have tripped some people up is this secant line. Noticing that N is not the point of intersection on the circle, and O is also not on the circle. So you can't call that a chord. It has a chord in it, but we can't name that chord because we don't have letters. Glitch on you too. Glitch, glitch, glitch. Any questions on number 2? And we shall go on to number 3. I don't think I was complete in listing all the possibles here. So if there's one you're not sure about that you got that I did not list, you are welcome to ask. And actually, you can go ahead and check number 4 as well. I'll explain that 6 in a minute. That 6 is not really part of the problem there. Yes, ma'am. Absolutely. Yeah. And that's what up here mentions YP. Remember, with segment names, you can go either way. So this could be QP, or it could be RP, or it could be PY. Yeah. Good call. Any others you guys want to ask about? On the tangent, ML is fine too. Yeah. How about any on number 4? We good? Okay, let's go ahead and jump into those notes. So these were already posted on your Google Classroom. If you have not pulled them up yet, you might want to do so. So like I said, today we're getting into tangent properties. And really they're not just properties, they're theorems. There's some, I guess, I don't know. We're just talking more about tangents, more definitions involving tangents, but also two theorems and specifically that we will use a great deal. The very first two on this sheet actually overlap with the one we did yesterday. We already talked about congruent circles and concentric circles. So those are what those first two are about. Would somebody in the virtual classroom speak so that I know my speaker is working on that?
Hi.
Thank you. Perfect. Yeah, for some reason, I was not able to hear someone last period, even though it said the speaker was working and everything. So it was very strange. And I could see that they were talking. Okay, the reason I underlined this word here is because on all of these, we're really talking about in the plane, because they decided to be a little bit more specific here, because technically, if we were talking about two circles and where they could intersect, if we weren't talking about in the plane, it could be all kinds of different things could be happening, meaning not in a plane means 3D. So this is just specifying that we're talking 2D. We're talking two circles that you could draw on your paper. Okay. All right, moving right along here. Let's see, what do we got next? Oh, we got tangent circles. These two circles are internally tangent because one of them is inside the other. And externally tangent circles are ones that touch, that are not inside of each other. They are completely external to each other. Okay, one thing to notice here is that tangent means the same thing whether we're talking about a line or another circle. The whole idea is they have one point in common. So just like with a circle and a line, two circles are tangent to each other. They have one point that is in both circles, or one point at which they intersect. All right, next up, we have common tangents. And don't write this stuff over here until I explain what that's about. I guess you could write exterior, interior. Okay, so there are actually, like when I have two circles like this, there are 4 different common tangents I could draw. Okay, so there's one here, there's one here, there's one here. So a common tangent is one that's tangent to both of them. And there's one here. So it means it touches both of them in one point. This little orange segment that I drew between the center of A and the center of B, That's the test for whether they are internally tangent or externally tangent, or interior tangents versus exterior tangents. Is interior or internal tangents, excuse me, an internal or interior common tangent, or my wording is off, sorry. A common tangent is internal or interior if it crosses the segment between those two centers. So that's the test. If it does not cross the segment, the imaginary segment connecting the two centers of the circles, then it's an external tangent. If it does touch that segment, it's an internal tangent, an internal common tangent. So that's your test for this. Now the next two, it was kind of in my opinion, on that particular notes page yesterday, a little bit of an oversight that we didn't talk about point of tangency yesterday, but I'm sure it's pretty much exactly what you would expect it to be. If we say that tangents is about having one point in common, then the point of tangency is that one point we have in common. Okay, so that's what that's about. The thing right below there on your notes that we're coming to is your first theorem on tangents, or the first major property that we need to talk about. Remember, a theorem is just a property of, or a math property, a math statement that can be proven. So I'm not like contradicting myself by calling it a property in a theorem, in case you're wondering why I'm jumping around there. Okay, so the point of tangency is that one point that the circle and the line have in common, or the two circles have in common. And then here's our big statement. The radius is always perpendicular to the tangent. Sometimes people will ask me which radius. Well, the radius at the point of tangency. So in other words, if I have a circle and I have a tangent line, let's say it's right here. There's only one point where they intersect. That point is therefore on the circle. Anytime I have a point on the circle, if I connect it to the center, that's a radius. So, and this one I didn't draw very well, but if we do that, then this is a right angle automatically. That's what this is saying. That's 90 degrees every single time, which means it is over here as well. Okay, so using that, a couple of different ways we're going to use it. First off, find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. Okay, so the radius of A, remember that when we're looking at figuring out distance and we're on a ruler or a grid or something like that, you're not counting the marks, you're counting the spaces. So the radius of A, if I start at A and go to the edge of the circle, anytime you have a circle that's graphed, generally, if we're trying to talk about the radius, you just count one of the vertical or horizontal lines, diameters. So in other words, count up, down, left, or right to see how far is it to the edge. So A, 1, 2, 3, 4 is my radius. The radius of circle B is what? 2. Good. What is the point of tangency here? Okay, remember a point on the coordinate plane, we have to have two coordinates, an X and a Y coordinate. 3, 0, you got it. There is my point of tangency. Now, on both of these are pretty easy lines to identify. We don't have to worry about the slope and the etc. because we have a vertical line, and over here we have a horizontal line. The equation of a vertical line always starts with what letter? It's easy to get them mixed up, so I don't blame you for being a little bit careful. Always starts with x. Equation of a vertical line is always x equals some number. Because every single point on this line that's what it has in common. Every single point on that line has an x value of 3. So x equals 3 is the equation of the line. Questions on that one? Okay, you guys go ahead and try B. Yeah. Okay. Why don't you check this real quick before you go there? We're just going to go through this real quick. So radius of C is what? 1. Good. Radius of D is 3. The point of tangent C and the equation of the tangent line. You got it. Okay, so let's go ahead and talk about, this is what I sort of was alluding to yesterday. This is like the main way we use this is to, well, we don't, no, let me correct what I was going to correct. One of the main ways we use this is to determine whether or not we have a tangent, because you can't tell just by looking. You can't just say, oh yeah, it looks like a tangent, so it is. We also use it when we know we have a tangent, but we need to find missing segment lengths and stuff. So basically, the idea here is if AB is a tangent, then that would mean that this has to be a right angle. Right now, I don't know if it is or not. They're asking me. If this is a right angle, that means this whole triangle is a right triangle. What does that mean should apply then? Pythagorean theorem. Okay, so I'm going to use the Pythagorean theorem to see whether or not it's a right triangle, which is the same as checking on whether or not this is a right angle. So I'm going to do 8 squared plus 12 squared, because those would be my two legs. And then I'm going to do 17 squared, and I'm going to compare those things and see if it's an equivalence relation or not. Okay, so when I do that, this is what I get. That 8 squared plus 12 squared is 208, but 17 squared is 289. So those are not equal. So it's not tangent. And you do need to do what I've done here in terms of like showing your thinking as well. Like, how do I know it's not tangent? Don't just say yes or no. Okay, show me that either the Pythagorean theorem works or it does not work, one of the two. Because if the Pythagorean theorem works, that means it is a right triangle, so that angle is a right angle. If the Pythagorean theorem does not work, then it's not a right triangle, so that angle is not a right angle. So go ahead and check B. Okay, so is the second one yes or no? Yes. Okay. I would say yes, it's a tangent. And I would show that my reasoning is because 20 squared plus 21 squared is equal to 29 squared. You can put a little check mark to show you checked it or just not. All right, here's our second theorem about tangents that we frequently use. It says if two segments are tangent to a circle from the same exterior point. So that says exterior. I was going to put the word point in here, but here's the word point over here. So in other words, point A is my exterior point. Then the segments are congruent. I like to call this the ice cream cone theorem. If you think about when you get an ice cream cone, if you were going to get a perfect sphere of ice cream on top of it, it would be a problem if one side of the cone was much shorter than the other because the nice sphere of ice cream would go toppling off in that direction. The two sides of an ice cream cone have to be the same. So that's why it looks kind of like an ice cream cone turned sideways. Here's my ice cream cone. Okay. So yes, these two segments, these two tangent segments will always be congruent. Any two tangents to the same circle that meet at a point outside the circle are going to be congruent. So that means here in A that I can say that DE has to be the same as DF. So that means 5y minus 28 has to be the same as 3y. And then I can solve and find DF, which is what they've asked me to do. So go ahead and finish that one. Okay, so when I solve here, I get 2y is 28, y is 14, and that's not what I was asked for. I was asked for the length of DF, so I could plug into 3 times 14 and get that DF is what? Is 42. Okay, go ahead and try B. Pretty much the same exact principle. Ice cream cone theorem at work. None of these equations are any different in terms of geometrically, in terms of setting them up. What's different is this one's a little bit trickier algebraically, you know, or arithmetically, really. Let's look at this algebraically real quick first, before we do anything else here. I just want to point out the various ways you could approach this, because they're all ways you might want to approach an equation at some point. One way you could approach this is you could approach it like it's a proportion. Say this is the same as this over 1, and you don't have to write the over 1, But if I multiply 4 times this, I get an equation that's easier to work with. Cross multiply. That's one way. Another way to look at it is if I have division, I want to get rid of division, I can just multiply both sides by what I'm dividing by to get rid of that division, which is really the same thing. You end up in the same place, 4 times that quantity. Okay. Couple of other ways you could look at this. When you have fourths, it's not usually a great idea to change fractions to a decimal if you got fractions, but number one, this problem already has decimals, so that kind of makes it legal. Number two, fourths are really nice, clean, tidy decimals. They're not like, repeating decimals. So I could change this. This is the same. This means this. So I could change it to 0.25x. And then just solve it as usual. Okay. And another thought I want to give you here, because it goes with these two, is anytime you have an equation that has denominators, and you don't want it to have denominators because you don't like dealing with the fractions, you can very easily get rid of the denominators by multiplying by something they all go into. Okay. And anytime you multiply an equation, anything you're doing, you have to do both sides, right? So I could take this entire equation and go, I don't want a 4 in the denominator. I'll just multiply both sides by 4. It'll go away. You could even do that for more complicated situations, like if you had, I don't know, something like this. You can say, I don't want any denominators, but both of those numbers go into 6, so I'm going to multiply both sides by 6. And when I'm done doing that, I won't have any denominators. Because 2 goes into 6, so this would just be 3x. And 3 goes into 6, so that would just be 2x. So that's a nice strategy. Any which way you do it, what are you going to get for x at the end? I agree. 8.4 is what you get for x. Okay, so whichever way you work it out here, you get x equals 8.4. But you have to remember that that's not what you were asked for. You have to go plug it into RS to get your answer. Helpful hint, if it's easier to plug it into RT, remember the whole point here is they're the same. So you could plug it into RT instead. You could just do 8.4 minus 6.3. Or you could do 8.4 divided by 4, because it's very neatly divisible by 4. And you get RS is 2.1. Questions on that? If you got stuck on the way you were working it out, you might want to, I'm glitching here, sorry. You might want to go back and work it out one of these other ways. Okay. All right. RT and RS are tangent. This one's very straightforward. Have you already done it? Yeah? No? Okay. So what do you get for n when you do this one? You get 4. Probably. I haven't done it. So let me just run through it real quick. Yeah. You get n is 4. And then you go back and plug it in because you need RS, and you get what? 7. Okay. Questions there? Okay, so I couldn't find a notes page that had all the types of problems I wanted to go over with you. So I'm going to give you a few additional problems here. Literally few. I think it's 3. 1, 2, 4. So that you've seen these types of problems. So I've got 4 more problems for you to try. And then you'll be free to do your homework, which should be very quick and simple. Because basically it's problems just like what we've done so far in the notes. So here is another problem. What number were we on? We'll consider this, well, that's not really example 3. Actually, this really goes more with example 2. So I'm going to call it example 2C. Like the numbering really matters a whole lot, I know. Or lettering or whatever. Example, not exam. Remember, you cannot look at this and say, yeah, look, it only touches at one point. You have to actually mathematically figure out whether or not that's a tangent segment. I think I need to go a little further away. Sorry if I'm making you seasick. Look away. There we go. Now I can bring it up a little bit. Is that better for the people in the back? I'll do that too. So y'all should be writing this down. This is still part of your notes. Is it tangent? No. Let me talk to you about how we could tell that by looking at it. And this problem actually is a little bit easier than I originally intended. Because it's an isosceles, because AB and BD are the same length. If this was a right angle, then that would be a 45, 45, 90. So if this is 5 and this is 5, this would be 5 root 2. Is 5 root 2 the same as 7? No. Okay, so that's one way we know that that's not going to be a right angle. Okay, questions on that one? Next one's very similar. We'll call this 2D, if you want to call it anything. this a tangent? Yeah, it's actually a Pythagorean triple we just worked with on another problem, right? 20 and 21 can be the legs if 29 is the hypotenuse. So yeah, this is 20. If you did 10 squared, you didn't realize that that's only the radius. Remember that when we have a measurement for an object, well, a measurement for a segment is generally centered in the segment, centered on the segment. So this 10 is right here. If I wanted to tell you the entire length of DB, I would either have to tell you both of these lengths or like write it out to the side with something that indicates it's the whole thing. Okay, so this is only CB, which means this is also 10, which means that's 20. Questions there? Next up, and this goes more with example 3, so we'll call this 3D. I'll make it come at you. 3D. Just kidding, sorry. Didn't want to make anybody sick. Okay, what'd you get for X? 1, exactly. Okay, let me just go ahead and do this one. You have 5x squared plus 9 equals 14. And there's a reason I want to do it for you. And that is to point out that really when I'm solving this, I get plus or minus 1. But what I'm doing when I say it's only 1 is I'm discarding an extraneous solution. An extraneous solution is one that you get by doing the right thing, but it doesn't actually work for that particular problem. And it wouldn't work for this problem because then I would have, if this was, well, actually that's not true. I'm lying. It does work for this problem. Both answers are correct. I apologize. What I was going to say was when I plugged it back in, I get a negative number. No, I wouldn't because it's squared. If X was not squared, that would be the case. But if I plug in a negative 1 here, negative 1 squared is 1. 5 times 1 is 5, plus 9 is 14. So 1 and negative 1, you get 2 solutions that are both correct here. Okay, questions on that? So I gave you the wrong answer and then talked myself back into the right one. But I did want to point out that don't forget, whenever you take the square root of both sides, that gives you a plus or minus automatically. I don't think when I was in high school, I understood why sometimes we would say plus or minus and sometimes we wouldn't. And when we're taking the square root, and if I haven't talked about that before, let me tell you that the big idea is if there's already a radical, what's considered the positive root. Like if you see a problem and in the problem it says something like this, that means the positive root of 16, so that means 4. Okay, but if there was no square root already there and you have to add 1 to take the square root of both sides, when you're the one that introduces the radical, then there's a plus or minus automatically has to go in there. Okay, last one and the most interesting of these extra problems. I wrote these so big it makes it hard to show it all well. You are finding the perimeter of triangle ACE, the circumscribed triangle. Okay, so the key thing here is that you've got ice cream cone theorem going on 3 times. Okay, that's what's going on when you have a figure inscribed, a circle inscribed in a polygon, or a polygon circumscribed about a circle. You've got a bunch of tangents. You got a bunch of tangents that come from the same exterior point. Yes. Question?
You stopped sharing your screen.
That's weird. Okay, thank you. Recently or a long time ago?
Oh no, like right now.
Okay, good. Thanks. Appreciate your telling me. Can you see it again?
Yeah, thank you.
No problem. So like this and this, there's your ice cream cone. Those would have to be the same. And this would also be the same. Hold off. Let's finish this problem. That would be the same as that. That means that this segment here is 12 minus 4, which is 8. And then I can go ahead and add up all the sides, and I should get I believe 37. Is that what y'all got? Yeah, okay. All righty. So the homework is maybe going to take you like 10 minutes, honestly, probably. And that's it for the weekend. And I will see you guys on Monday. 4, 5, 6, 7, 8, 9, 10. We need to clarify what I mean when I say hold off, because 10 people left before the second bell when I said we were going to wait. Okay. We're actually not out of class on the second bell. So. Ella, I have to tell you that I am really, really bad with thank you notes. So I want to thank you for your awesome, awesome Christmas present. You're welcome. This was really, really very excited to get, especially because I don't know when you left it here, but I got it right after the break. Oh, really? And so it was when I'm not used to, I'm done with, thought I was done with gifts. And then they're, I got gifts. I mean, I left them off before the break. Well, I just, they must have, maybe they put it in my box like right before we left and I didn't check the box again or something, but I was like, woohoo. So nice to come back to. I'm just sorry. I'm sorry that Steven's just sitting here listening. I just realized to our conversation. Unless Steven has checked out. Yeah, I think he has.